We're going to go over a related rates question today that has to do with a cone. And in the end, this one is going to have to do with similar triangles. Well, not in the end, and actually in the very beginning. So I'll give you a couple minutes, or you might want to just shut the video off to write down this question. It says a container has the shape of an open right circular cone. So here's the diagram of the open right circular cone. The height of the container is 10 centimeters, and the diameter of the opening, this diameter right here of the opening, is also 10 centimeters. So all the way across here. There's water in this container. This represents the water down here. The water in the container is evaporating so that its depth H, which is indicated here, this is the depth of the water, is changing at a constant rate of -0.3 of a centimeter per hour. They give you the volume of the cone. How nice of them. And then what they want is a couple things. First of all, we're going to find the volume of the water when this height is equal to 5 centimeters, including the units of measure. Well, the reason why this has to do with similar triangles is because if you have a right circular cone, what you can do is you can just drop from the very center of the base of this cone, you can drop this straight down to the tip. And what you've created is you've created a triangle up here, a larger triangle. And what we know about this triangle is we know the height is 10, and we know this base right here is 5 since they give us the diameter as 10. So I'm just going to cross out that 10 and put 5 here. So we have a 5 and a 10 here. And now what we have is we have a similar triangle down here, which is smaller. And this is the base of the water. And it goes down to the tip of the water. And because these are similar triangles, you can say that the sides are in proportion. So 5 over 10 is equal to R over H. So in other words, 5H equals 10R, or in other words, the height of this is always equal to 2 times the radius. And that makes sense because here's the height is 10 and the radius is 5, so the height is 2 times the radius. Well, the reason why I'm solving this for H is equal to 2R, or actually we could also say R is equal to a half H. That might be a better thing to do in this problem, because what they give us is they're giving us that H is changing at the rate. So that means we've got, oh, I should probably write a pen. So that means we have dH dt given to us is -0.3, or I'll call that 0.3 centimeters per hour. Part A says find the volume of the water in the container when H is equal to 5. Well, if H is equal to 5, the volume is 1/3 pi r squared H. So V is equal to 1/3 times pi. Now if the height is 5, then the radius is 5 over 2 pi r squared times H, which is 5. So all we have to do is multiply through. 5 squared is 25, times 5 is 125. So we have 125 pi all over 3 times 4 is 12, because you have to square the 2 also. And the units of measure, well, the volume is in centimeters cubed. So that has nothing to do with related rates. They just want to know, they want to make sure that you can use similar triangles to set up this volume formula to find a volume. Now what we have to do is use a little bit of calculus to find the rate of change in the volume of the water. Excuse me. with respect to time when the height is 5 centimeters. So this is where the related rates comes in. So what we're going to do is, because we've already set this up in terms of solving for R with H, we can use this volume formula, V equals 1/3 pi R squared H, but we already know that R is equal to a half H, so we can replace this R with a half H, and then we'll have everything in terms of V and H, because what they want to know is the rate of change of volume. So they want to know dV dt. We're given dH dt, so when we take this derivative implicitly, we're going to have a dH dt in there, and we can replace that with a 0.3 centimeters per hour. So the R is just going to come out of there because we've already solved that. So let's call the volume 1/3 pi. Now R is a half H, so we have 1/2 H squared times H. And what that is, what that volume is 1/3 times 1/4, which is 1/12, and you have a pi in the numerator, pi over 12 times H squared times H, which is H cubed. So there's the volume. And now once we get the volume formula, we can take the derivative, dV dt is equal to 3 times pi over 12, which is pi over 4, H squared dH dt. And now they want to know what the rate of change of the water is when H is 5, so we're going to substitute a 5 in here, and dH dt is going to be equal to 0.3, or 3/10. So we have pi over 4 times 25 over 1 times a negative 3 over 10. Excuse me. And I think we can reduce this down. 5 goes into 10 twice, 5 goes into 25 5 times, and I think that's about it. So the rate is negative 15 pi all over 8, and the units of measure, this is a change in volume over time, so this is centimeters cubed per hour. Here's another related rates example that has to do with similar triangles, and this is a trough question. Not sure if you're familiar with a trough, but they've got a nice picture of it down here. The trough shown in the figure is 5 feet long. Its vertical cross sections are inverted isosceles triangles. So here's the isosceles triangle that they're talking about. Inverted just means it's upside down. And it says it has a base of 2 feet, so it's indicated here as 2 feet. I'll show you over here. Its base is 2 feet, and the height is 3 feet. Now what's happening with this trough is there's water down here at the bottom of it, and water is being siphoned out of this trough 2 cubic feet per minute. At any time t, we're going to let h be the depth of the water. So this little height right here is the h value, and v is the volume of the water in the trough. So the trough is not full in this picture. It's only like a third of the way up. And what they want us to do first is find the volume of the water when the trough is full. So if this was all the way filled up, they just want to know if you know your geometry. And your geometry says that if you want to know the volume of this, the volume is just the area of this base times the height. And you might think about it as like having it up on its end. And if this were flat on the floor and you were measuring this, you'd measure the area of this triangle, which is 1/2 base times height, and then you would have to multiply it by the length of this, which is 5. So the volume, if it's full, volume of that trough is equal to 1/2 times base, which is 2, the base of the triangle, times the height of the triangle, which is 3, times the length of this side, which is 5. So the 2's cancel out, and all you're left with is 15. No pi in here because it's not circular. So this is 15 cubic feet. All right, the next question is, what's the rate of change in H? So in this little part of it, H, at the instant when the trough is a quarter full by volume. So if it's full, it's 15 cubic feet. So if it's a quarter full by volume, the V value would be 15 over 4 cubic feet. So that's what I want the instant that H is that tall, and we'll figure that out in a couple minutes. So now what we want to do, rate of change of H is what they're asking for. So they're really asking us for dH dt. We don't know what that is. But they're telling us in the problem that the water is being siphoned out of the trough at 2 cubic feet per minute. So that's the change in volume over time. And we have to make this negative 2 cubic feet per minute. And it's negative because the water is going away. It's being siphoned out. If it were being filled up, it would be positive, but because it's decreasing, it's negative. So now what we want to do is we want to relate the variables with each other. Now over here, there's a picture of the end of this water. This is the water end here. And the whole trough is two across and three high, and then here's the water part of it. This length, we'll call it B, and this height, we'll call it H. Well, what we have again is similar triangles. We have 2 over 3 is equal to B over H because the sides are in proportion with each other. So that's just the similar triangles part of it. This is the whole end of this trough. And then this is the similar triangle part of it. So 2 over 3 is equal to B over H. And because they don't really say anything about B in this problem, we're going to be solving this for B and have everything in terms of H because they want dH dt, so we're going to have H's in our formula in the end, only V's and H's because that's really all we know about in this problem. So now what we're going to do is we're going to find the volume of this water as a formula. So the volume is equal to 1/2 base times height times 5, because the trough is 5 feet long. So we've got the base, which is B. We don't know how big that is, and the height is H. And because we know that 2/3 is equal to B over H, we can do some cross multiplying here and get 2H is equal to 3B. Or in other words, we want to take B out of there, so 2 over 3 H is equal to B. So we're going to replace that B in our formula. 1/2 base, which is 2H over 3 times height times 5. And I don't know why I'm writing uphill, but I'm writing uphill here. All right, so there's our volume formula, and I think we'll just clean this up a little bit by taking those 2's out of there. And it looks like we've got H times H, which is H squared. So the volume is equal to 5H squared on the top and a 3 on the bottom. Now what we want to do is take the derivative of this. So we're going to get dV dt is equal to 10H over 3 dH dt. But we're going to have an H in here that we're really not sure of what we're going to replace it with. But it says that we want to find the rate of change of H when the trough is got a volume of 15 over 4. So what we need to do is we need to solve for H. So when we take the derivative and need to replace it, we're going to be replacing it with a number. So this volume is 15 over 4. We're going to solve this for H. That's from the very beginning part here. So we can just do some cross multiplying here to solve it for h. 3 times 15 is 45, so I'll get rid of that 3 and call this 45. And then divide both sides by 4. 5 times 4 is 20. So we have 45 over 20 is equal to h squared. So h squared is equal to, if you reduce 45 over 20 down, 5 goes into 45 9 times, and 5 goes into 24 times. So the h value is equal to the square root of 9/4. So in other words, h is equal to 3 over 2. So that is the value that we're going to be plugging in to our derivative after we find the derivative of this, where's the formula right here? V equals 5/3 h squared. So let's go back to that one. V, oops, I'll move that up here. The volume. The formula for the volume way back when was 5/3 h squared. I believe that's what we had. Yes, 5/3 h squared. So now we're going to get dv dt. 2 times 5 is 10 thirds h dh dt. And they want us to find dh dt. That was the original question back when. And they said dv dt is -2. So -2 cubic feet per minute is equal to 10 thirds. H is 3/2 dH dt. So the 3's cancel out. 10 over 2 is equal to 5. So -2 over 5. And what do we have? This is a change in height over change in time. So we have feet per minute is equal to dH dt. Oops, I'm still running off, sorry. -2 over 5 is dH dt, and that's what they want. That is the change in height. So the height is dropping 2/5 of a foot per minute. And then the last part, it says, what is the rate of change of the area of the surface of the water at the instant when the trough is 1/4 full by volume? So the area of this water right here, well, this is B, and this is 5. So the area is just 5B. This is part C here. So area is equal to 5B. But way back when we said that B is equal to 2/3 H. So we have the area. The area is equal to 5 times 2 is 10H over 3. All right, so let's find the derivative of this. dA dt is equal to 10 thirds dH dt. Well, dH dt turned out to be -2/5 in the previous problem. So we're just going to find dA dt is equal to 10 thirds times -2 over 5 from the previous part of the question. So 10 over 5 is 2. And then we've got the change in area is equal to -4 over 3. And area is in square feet per minute. And that's the end of this problem. Have a nice night. See you tomorrow.